This is lecture 3, part 1 for Introduction to Systems Engineering and for System Thinking and Analysis, which is the graduate course for this class. And this is the first part of this lecture. And in this lecture, we're going to talk about the hierarchy in terms of the different levels of components for a system. So as always, we start our lecture. I like to point out where the material that is presented in these slides is coming from. So in this case, this is material from your textbook, Systems Engineering Principles and Practice. And the agenda for today is the following. We're going to start with the discussion of the systems development process. Then we're going to discuss the systems engineers' technical knowledge. Then we're going to transition to the hierarchy of complex systems. And finally, we're going to talk about the concept of systems of systems. So let's get started with the system development process. In a major system development includes the following characteristics. So as we have discussed already as part of the class, it has to be a major effort. And also it has to meet some type of societal need. So this is something that is going to make a difference in terms of helping a community or helping a specific group, or maybe overall the whole society. So it has to have some type of connection with the society. It is an effort, a major effort, so evidently it's going to require a lot of time to be completed. So we are not talking about a project that you can accomplish in, let's say, 2 months, 3 months. This is something that takes a lot of time. Like we are looking at, for example, the missions to Mars right now. So our end goal is to be able to bring people to Mars, but it is a major effort that is going to take some time. So now we are doing the exploration. We have the robots. We are looking at the planet itself through the camera. We are trying to learn. We're trying to learn the conditions, and then based on that learning process, then other developments are going to happen, and at some point, that major effort is going to be completed, which is to get people to Mars. It is made of interrelated tasks. So again, going back to this example of the mission to Mars, you have people from different backgrounds working together. We have experts in geology, we have experts in aerodynamics, we have experts that are well, many different disciplines working together with multiple interrelated tasks. And again, the multidisciplinary teams is also we have been mentioning this from the beginning. You have people with different backgrounds, different expertise, and they have to be involved in order for this major effort to work. And oftentimes is something that is performed by different organizations. Like if we talk about NASA, we know there's some ongoing collaboration with some private organizations as well, like SpaceX and so on. So performed by different organizations, I mean that you open the door for people that have some advantages in terms of technology, or you have people that are experts on specific, like let's say community programs that have access to the people, and you're trying to solve a problem, but you don't necessarily have the interaction with the users. So you bring these other organizations that can help you get the feedback from the users, and then you can implement that as part of your project. And finally, it has to be within a schedule. So it's going to take 5 years, 10 years, and also within a budget. So how much money we have to get this done. So these are the characteristics. A major system development includes all the following characteristics, and those are the ones that are listed in this slide. So the system development process based on Bahill, he described the system development process as it is a parallel and a highly iterative process in which we have a customer needs, and then based on those needs, we have an output for our system. But as you can see in the top figure of this slide, there's the multiple loops here. You start stating the problem, and then you move forward to investigating alternatives. But at the same time, if you learn more about the problem, you have to reevaluate your statement and then bring, let's say, you have new customer requirements, or maybe a user was not involved and now you have extra knowledge about the problem and you want to integrate that to your statement. So you reevaluate and you put that back into the problem, and then you move forward. And that's going to happen for all steps. So investigate alternatives, model the system, integrate, launch the system, and assess the performance. And in each one of these steps, you have these interrelated loops. That means that there's some feedback going on through the process. So what this is trying to illustrate is it is a parallel and highly iterative process, meaning that you have the reevaluation part happening simultaneously as the process is moving forward. So you learn, you apply, and then you revise, and then you move forward, again, learn, apply, revise, and move forward. So it is not a serial process. It's not something that you are going to throw over the wall. Now it's your problem, I'm going to start something new. No, it's a problem. It's a process in which everybody's going to get somehow involved until the development is completed. So it's not a serial process, a waterfall process, or not throw it over the wall process the type of process that we are accustomed. So I do my part, then I'll send it to this person and they will take care from now on. That's not the case for the system development process. Another important concept is the concept of the system life cycle. So if you have taken courses from, let's say, concurrent engineering or product development, you should be familiar about the system life cycle or the life cycle of a product, which means that you have different stages for the development, and in each one of those stages, there's some type of action or some type of measurement that you have to take. So the system life cycle refers to the stepwise evolution of a new system from concept through development and onto production, operation, and disposal. There are different life cycle models within the systems engineering professional discipline. There are the Department of Defense has their own, the international model or the ISO, and then the National Society of Professional Engineers also. So I will show you those in a minute, and you will understand that even though they have different steps, if you look at the step with attention, you will see that they are kind of the same, and they're trying to model this. At the end, they're similar. There are also software lifecycle models, which involve more iteration iteration, prototyping, and life cycles of other systems. So in here, you see the comparison of system lifecycle models. The DoD is at the top, and then we have the ISO on the second level. We have the National Society of Professional Engineers on the third, we'll say the third row. And then we have the systems engineer stages and the system engineering phases. Those are the ones defined for this class. Okay, so we have the top, at the top of this figure, we have the three that are coming from these professional or these organizations, and then we have the ones that are basically summarizing the whole thing. And these are the ones that we're going to use for our class, the system engineer stages and the system engineer phases. So as I mentioned already, you see that there's if you look at the, for example, DoD and the ISO, the ISO has two big steps or stages at the beginning: concept and development, and then production, utilization, and support. If you look at the DoD, they have a mission, need, and determination. That could be part of a concept definition. And the same thing for NSPE, you have conceptual, concept, mission, need, determination. So you're basically, and then the second step of the DoD actually have the word concept attached to it. So you see that at the beginning, you're doing the same thing. You're trying to define your concept, and you are trying to define the technical feasibility of those concepts. And then you move forward into the development, and then you move forward into the production, utilization and support, operation and support, and so on. So, so those are the top three, right? At the bottom, we have the class, the course, the system lifecycle model that we are going to use in this class. This is the one that you had to memorize. This is the one that you need to know, the 3 stages and the 8 phases of the system lifecycle model. So we have the concept development, and within the concept development, we have the needs analysis, the concept exploration, and the concept definition. So later this semester, we're going to go deep into each one of these phases. Same thing for engineering development. We have the advanced development, engineering design, integration, and evaluation, and then post-development, production, operation, and support. So for the purpose of the course project, you will see that we're going to focus on this concept development stage. For your project, you're basically going to do the need analysis, the concept exploration, and concept definition. We are not going to go into the development part, but if you were, for example, working for one of these large organizations like NASA or Lockheed Martin or any of these big companies that look at technology, after you do the concept definition, obviously you want to build something. You want to put it into the market, and you want to support that operation, and you want to make sure the post development as part of it. So again, first, seeing two things that you have to learn. You have to know the system engineering stages: concept development, engineering development, post development, and the systems engineering phases. Okay, so again, I want to make sure that you understand that you need to know this. We're going to be referring this back and forward in terms of the material that we're going to cover in this class, and also for the purpose of the exam. You need to learn this. You need to know this by memory. So this is the life cycle model. The system development life cycle, we can summarize this into the following. We want to understand the problem. Okay, so that's what we need, a needs analysis. We want to make sure that this is something that has some type of societal need. And in understanding the problem, we also want to know the requirements. So what's the user? What are the needs of the user? Well, how do we state those requirements clearly, so we know that we are defining and designing something that is going to be used, is going to serve the purpose. And then we move to the design. We have a preliminary design and then a detailed specification of our design. And after design, we look at building, right? Solution building, construction, verification, testing, integration, validation, and testing. And then finally, installation and use. So implementation, user acceptance, and maintenance. So here's some comparison about two other models, the system evolution process and the knowledge modeling evolution. If we compare this to what we just discussed, you'll see that there's some similarities. So again, system evolution process, you have the needs at the beginning, observation, need, development, transition, and then the build, operation, maintenance, enhancement, overhaul, decomposition, and disposal. And then knowledge modeling evolution. This is more from a theoretical point of view. Observation, classification, abstraction, description, specification, representation, explanation, quantification and measurement, symbolic representation, symbolic manipulation, decommission, and prediction. Okay, so now we're going to transition to the systems engineers technical knowledge. And what I want you to understand, or what I want you to learn from this part of the lecture, is that we get a study that there's multiple levels in the hierarchy of complex systems, but it's impossible for the systems engineer to know every single detail for all the levels of the hierarchy of the complex system. So what is important here is that we're going to explain up to which level of knowledge you need to have when you are developing a system or an engineer system. So a system engineer needs to attain a broad knowledge of several interacting disciplines involved in the development of a complex system. But how deep should the understanding be? Again, it's impossible for anyone to have a complete detailed understanding of every single component of your system. So it cannot be as deep as the knowledge possessed by the specialist. Okay, remember that you're working with multiple different disciplines. So it's impossible for you to have an understanding of every single discipline that is involved in your development. But it must be sufficient to recognize the following: program risks, technological performance limits, interfacing requirements, and also sufficient to recognize or make trade-off analysis among the different design alternatives. So you don't need to understand how, let's say, a screen on a particular area of your system is working, but you need to have a good understanding of how that screen is going to serve the purpose of the system. Okay, and that information or that type of knowledge is going to help you make a decision. Like at the end, you would have when you're looking at these challenging developments, most of the time you end up with different ideas or different concepts, let's say 2 or 3 concepts. And then you have to make a decision. You have to select one of the concepts to move forward. So having a good understanding or sufficient understanding of the system allows you to make those trade-off analysis. The structural hierarchy of modern system reveals the existence of identifiable types of building blocks, which make up a large majority of systems. This reveals the lower working level of technical understanding that the systems engineer must have in order to do the job. This is the level at which technical trade-off affecting the system capabilities must be worked out. And also, interface conflicts must be resolved in order to achieve a balanced designs across the entire system. So let's talk about the hierarchy of complex system, and then we can answer this question. I mean, well, how deep in the hierarchy? But we need to learn about the hierarchy first. So the hierarchy of complex systems. Complex systems may be represented by a hierarchy or hierarchical structure, excuse me, in that they are composed of. And these are the hierarchy. This is the hierarchy. We start at the bottom with the part. Then we put together some parts, and then we have a subcomponent. Put together some subcomponents, and then we have a component. Then we group some of the components, and we have a subsystem. We group multiple subsystems. We should have the system. And if this system is integrated with other systems, then we have what we call a system subsystems. So for example, if we look at the car, these are the different levels. So we can have, for the part, we can have wires. In terms of subcomponent, we can have the gauges. And then we have the instrumental panel. And then we have the car interior at the subsystem. At the system level, we have the car, and the systems of systems is the systems that the car interact with. In this case, garages and roads. So how do we differentiate between the hierarchy levels? Well, the parts are the elements that perform minor functions, except in combination with other parts. These may come in standard form and may be commercially available. Subcomponents perform elementary functions that are composed of several parts. Components are middle level of system elements described above. Subsystems are a major portion of the system that performs a closely related subset of the overall system functions. This typically involves several disciplines, and then the system is made up of interacting subsystems. Supersystems or system of systems are made up of interacting systems. So on the next slide, we have some examples. So at the top, we have the systems, and then next level, we have subsystem, next level, we have components, subcomponents, and parts. So at the top, we have the system. So if we go to the first column, we're looking at the communication system. One of the subsystems of the communication system is the signal networks. Components could be the signal receivers, and at the subcomponent level, we have the signal amplifiers, and then at the parts level, we can have a transformer. And then we can look at the other ones as well. So if we go to the last column, aerospace systems, then we have the engines. The component level, we have the thrust generators. At the subcomponent level, we have the rocket nozzles. And at the parts level, we have the seals. So in terms of our definition of a system, recall that to avoid ambiguity concerning the definition of system, we shall limit the use of the term system to those entities that possess the properties of an engineered system, as we define in lecture 1, and also perform a significant useful service with only the aid of human operators and standard infrastructures. So for example, power grid, highways, fueling stations, communication lines, and so on. So finally, we get to answer our questions. So what are the domains of the systems engineer and the design specialist? So if you look at this figure, there's a shaded area. That shaded area is what the systems engineer domain. So we have to have at least a deep knowledge up to the component levels. Everything below that, some components and parts, is the design specialist field, or the design specialist knowledge domain. Okay, so the intermediate system components occupy a central position in the system development process. The system components fit within the domain of the industrial design specialist, who can be adapted to a particular application based on a given set of specifications. Proper specification of components to define performance and to ensure compatible interfaces. Okay, so the next bullet is very important. So the systems engineer knowledge must extend to the understanding of key characteristics of the system components. Okay, so to that level, as shown here by the shaded area, up to the components level is the system domain. We need to have a good understanding at the system, subsystem, and component level. Interact with design specialists. So if you have that knowledge, then you'll be able to interact with the design specialists to select the most appropriate types and specify their performance and interfaces with other components. Okay, so again, that's very important. So the knowledge must extend to the understanding of the key characteristics of the system components. Good, so one more item for today's lecture, the discussion of the systems of systems, or super systems, or system of system was coined in network military systems and is used to describe integrated distributed sensors and weapons systems such as those in a modern Army, Navy, or Air Force task force. The definition of systems is applicable to different levels of aggregation of complex interacting elements. So if we look at these examples, are the following systems, subsystems, or components. So the city telephone system, the telephone substation, the hotel and office building switchboards, and the telephone instruments. So obviously at the top we have the system, telephone, substation will be a subsystem, hotel, office building and switchboards, that will be a component, and telephone instrument, that will be a subcomponent or maybe a part. Same thing for air transportation system, that will be the system. Commercial airliner, that will be a subsystem, and airframe engines control, that will be components. So different ways of representing systems of systems. So we can use a pull check diagram as we discussed already. Here in this figure, we have a military group as a system of systems. So we have the fighting element, we have the command and control, we have the support elements, and the military group. And then the International Coalition Defense Organization. So again, multiple systems working together, ones with some capability that the other has, doesn't have. So so put it together, system of systems, we end up describing how the whole thing is interacting. Okay, so that's the last slide. So please let me know if you have any questions via email, or you can log into the question session during the class time period. Bye-bye.